Morning. Hey guys, good morning and welcome.
Morning.
Morning.
Good morning. Now, before we continue, any questions so far? Anything that we talked about yesterday that you guys didn't understand?
No.
Oh, let's do it this way. Zinka. So we started talking attenuation, and what did we say attenuation was? Because it's okay, a decrease in power and intensity and the amplitude. Okay, and just okay. Further explain that because it's okay as the sound wave. But okay, we said okay as we had vectors of attenuation, which were flatland. And we established the fact that that was going to be directly proportional to our attenuation. We also said another factor was the frequency. I guess it was okay, frequency of the sound wave. Okay, which is determined by the transducer, and that as well was going to be directly proportional to attenuation. Okay, then we had processes of attenuation, which was reflection, and we can mean says okay, the reflection here is okay, that's going to is okay, reduce the image or the scanning that you're getting. The next one that we talked about was scattering. Okay, and we mainly said that that was mainly as okay, directly proportional to the frequency. It's mainly as okay, you can say it's okay, explains why frequency of the sound wave is causing attenuation because of this. Yep. Okay. Now the last process that causes attenuation is what we call absorption. Clear? Okay. So what is going to be absorption? Now we can say, yes, okay, we have a transducer, that transducer, yes, okay, put, okay. And we have tissue media, for instance. Now what this transducer here does, it sends out a sound wave. Clear? Okay. Sends out a sound wave that travels towards a tissue boundary. We already said that, okay, some of that energy carried by this sound wave here is going to return back. So that will be, yes, okay, our reflection. Yeah, okay. And all dependent upon, it's okay, the amount of sound energy that is being reflected, that is going to create a certain shade or shadow on our image. Another thing we said was that we can say it's okay, scattering. And the last but not the least is that, okay, as this sound wave here, maybe it's okay, it travels through this tissue. What is going to happen is that some of the energy that is carried by this sound wave here is going to be absorbed by the tissue. Yeah, okay, and that will mainly mean that, okay, so that will mainly, yes, okay, lead to that the intensity of the sound wave that proceeds after passing this tissue here is reduced in our power, intensity, and amplitude, which will be attenuation. Okay. Now the question is, okay, yes, what is going to be, yes, okay, the effect of this absorbed energy that is being absorbed by the tissue? Now, one thing that it does is okay, we can say, okay, it reduces the intensity or, okay, yes, power or amplitude of the sound wave. And that was what we call attenuation, which was an example of what we call as, okay, the acoustic propagation property. Did that make sense?
Yep.
Right, okay. Okay. So what would I mean? What would be attenuation? That, okay, yes, this sound wave here, it's okay. The sound wave before it hits the tissue has a greater power, intensity, and amplitude versus this one here having a lower power, intensity, and amplitude. So that would mean, yes, okay, what we call attenuation. That was the effect of the tissue upon the sound wave. That the sound wave got affected by the tissue through which it passes. Clear? Okay. Now, to begin with, yes, okay, this here, yes, okay, was a sound wave, which means, yes, okay, will carry, yes, okay, what we call, or be, yes, okay, in the form of sound energy. Clear? Okay. Now, when that energy is absorbed by the tissues, okay, now there's a theory, another theory, there's a law of physics, which means say that, okay, yes, energy is able to change its form. So, okay, the sound wave that, okay, yes, were absorbed by the tissue. It's not going to remain as a sound wave. Okay. But actually it's just going to be converted into heat energy. For the sound energy that was okay, the sound energy that was absorbed by the tissue actually is going to just okay get converted into heat energy. Now we can mean says okay, this heat energy here is okay, that's going to lead to okay what we can call tissue warming. And as a result of that tissue warming, that's going to lead to yes, okay, what we could call a biologic effect or bio effect. Yeah, okay. Now, what did we say that a biologic effect or a bio effect is or was? That was the effect of the sound wave upon the tissue. Clear? Okay, but mainly because okay, as the sound wave, yes, okay, as it passes through, yes, okay, different tissues, greater or lesser amount of sound energy is going to be absorbed by the tissue. That greater or lesser amount of sound energy is going to be converted into greater or lesser amount of heat energy, which will cause a greater or lesser warming up of the tissue, which will lead to, yes, okay, cause, or we can call it bio effect or biologic effect. Because this tissue warming here, yes, okay, may, yes, okay, affect the tissues. So the effect that the sound wave has upon tissues is an, okay, or what we call a bio effect is another result of the absorbed energy. Did you guys get that?
Yep.
Okay. Okay. Now, out of all the tissues that we have, out of all the tissues, or different tissues that we have, the tissue, the kind of tissue which is going to have the greatest degree of absorption of sound wave is going to be the bones. Or we can mainly, as okay, just put it this way that okay, yes, the denser tissue, the more energy is it that it will absorb. Did you guys get that? Yeah, okay, okay. So of all our tissues, that's okay, the tissue in which we have the greatest amount of absorption is going to be the bones. Lesser tendons, lesser muscles, and so on, so on, so on, so on. Did you guys get that? Okay. So what is going to, yes, okay, what can happen is that due to, yes, okay, the increased amount of, let's say, yes, okay, sound energy being absorbed by the bones, there's going to be, yes, okay, an increased warming up of the bones or bone tissues. Clear? Okay. Which is going to, yes, okay, heat up. But then it comes as, okay, how resilient is it that the bones are going to be as, okay, to the amount of sound energy that is being absorbed, or as, okay, heat. Clear? Okay. So bones is okay as a stubborn tissue where it's not easy for it to, yes, okay, get affected by temperature changes. Other tissues, like I said, okay, liver, muscle, smooth muscles, or other kind of tissues that's okay are going to be as okay more sensitive to temperature changes. Okay, where a lesser rise in temperature, yes, okay, may lead to bio effect or biologic effects. Okay, but it may go that okay, as sound being absorbed by the tissue, that absorbed sound energy is converted into heat energy, and that heat energy can lead to what we call bioeffect or biologic effect. So the effect that the sound has upon the tissue was a bioeffect. The effect of the media upon the sound wave was what we call the acoustic propagation property. Clear? Okay. Any questions? Okay. And again, yes, okay. Just the relationship, because yes, okay, there is a relationship here. Okay. Between, yes, okay, we can say, we can put this way and say, yes, okay. Absorption. Now, absorption is going to be directly proportional to the frequency, which mainly means that, okay, as have we had two similar tissues? Clear? Okay. Two similar tissues being scanned by, well, okay, as two different transducers. Where we can say, it's okay, one of these transducer here has a, we can say, it's okay, that there will be a, okay, a low frequency versus a high frequency. Clear? Okay. What was going to happen is that it will be the tissue with the, there will be the tissue scanned by the high frequency transducer that will have greater absorption. And it tries to get, okay, being scanned by the low frequency transducer that will have lesser absorption. Although, yes, okay, they were the same tissues. Did that make sense? And then we can mean it says, okay, greater absorption is okay, what would that lead to? That will lead to, is okay, greater heat production of the tissue, or tissue warming, if that way you want to call it. Okay. And the more, yes, okay, tissue is getting warm, yes, okay, the greater is going to be the likelihood of biologic effects. That more heat actually is okay, has a greater likelihood of affect the tissues. Okay. But guys, in ultrasound, biologic effect or bioeffector is mainly, it's okay, more theoretical than actual. Okay. It's more relevant if you go to other scanning modalities like X-rays, CAT scans, MRIs, PET scans, and things like that. Because what those are they are mainly going to be high energy testing. Clear? Okay. The other thing is that, okay, yes, most of the energy that we transmit to the patient in an ultrasound gets reflected back. So there's not much energy left in the patient. Clear? Okay. Whereas, for instance, okay, for an X-ray, okay, whatever energy doesn't pass through the patient, it's going to hit. That's okay. Whatever energy passes through the patient will hit the X-ray film, and okay, yes, affect that film to a certain extent. Okay. So yes, okay. Most of that energy is okay get absorbed just by the bones. It's the same concept that bones would have more absorption. Okay. But then on those scans, that's okay, that tissue will look like it's going to just okay appear white. where, okay, any tissue through which the rays are able to pass through will appear black. Now, any questions? So, no matter what, when we compare the intensity of the sound wave here to just, okay, where it may be here, or the power, or the intensity, or the amplitude, the comparison of this versus what it would be over here, okay, that will mainly as, okay, mean that, okay, it will have decreased, and we call that decrease attenuation, and that is going to be expressed as, okay, yes, and using a common unit of decibel. As you said, which was mainly as, okay, a comparison of what we started with versus what we end up with. Okay. So, guys, this was, yes, okay, mainly, yes, okay, just the primary introduction to your attenuation. Okay. But please, 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 I hope that you have understood by now that attenuation is only going to be the change of your power, which will change the intensity, which will change the amplitude. And that change is going to be a decrease in those three bigness parameters. Yeah, okay? Your attenuation is directly proportional to the frequency. Your attenuation is going to be directly proportional to your frequency. Okay, but that does not mean that your frequency also changes as the sound propagates. When we say that it's directly proportional to attenuation, that's going to mean higher frequency transducers will attenuate more, lower frequency transducers will attenuate less. Clear? Okay. And the greater your attenuation, the lesser the penetration. Clear? Okay. The lesser the attenuation, the greater the penetration. Clear? Did you guys get that? Okay, so you can also just, okay, relate as, okay, attenuation, penetration to frequency. Clear? Okay. But you can again say it's, okay, higher frequency, less penetration, lower frequency, greater penetration. Okay. But the frequency of a sound wave is, okay, produced by a transducer. If it was 5 megahertz, it will remain 5 megahertz throughout. Clear? Okay. There's nothing new here. It's mainly as, okay, what we already talked about when we did frequency, that, okay, frequency is determined by the source and the source only. Clear? Okay. Now, guys, any questions about attenuation so far? Any doubts? Okay. Now, we can mainly say, okay, that there will be two methods or two ways in which attenuation can be, you can say it's okay, documented or calculated. Okay, and that's going to be as okay our next two topics. How is it, or what are the two ways in which we can express attenuation or document it? Because okay, this was just okay, the initial theoretical part of it. Okay, okay. But as we know, as a sound wave travels just okay, you can say it's okay 1 centimeter. The first centimeter that it travels through, for instance, skin, then you have fat, then you may say, okay, a little bit, okay, it's okay, connective tissues and so on. So all depending upon it's okay, the area that you scan, you may say it's okay in some instances, okay, you may even come across bones in that first centimeter that the sound wave travels, right? Clear? Okay. So it's not going to be that you'll be able to just, okay, practically, yes, okay, calculate how much is it that, okay, as each of these tissues here is going to attenuate the sound wave. Okay, so that's why it's okay, there are going to be two, yes, okay, kind of, okay, as parameters in which we, yes, okay, talk about the degree or, okay, an overall degree of attenuation of the sound wave. Okay. Now the first one, now we can mean yes, okay, see. That one is going to be yes, okay, what we will call an attenuation coefficient. Yep. Okay. The other one is going to be yes, okay, what we will call a half value layer thickness. Okay. But what both of these here are in common is that they mainly as okay are just matters of, you can say it's okay, expression. That's okay. The degree of attenuation of the sound wave. Is that clear?
That says expresses the degree of attenuation of the sound wave?
Yeah. Both
Okay.
of them are going to be methods by which we as okay can talk about how much, not necessarily numerically, okay, but how much is it that okay as sound as okay will attenuate? Clear? Okay. Okay, so we can talk about is okay, what we'll do is going to be attenuation coefficient. The other way is okay, in which it's okay, your attenuation or the degree or amount of attenuation that the sound wave undergoes can also be as okay, looked at as what we call a half value layer thickness. Is that clear there?
Yes.
Good. So let us just first of all talk about us, okay, what in the blue is it that an attenuation coefficient is. Now, before we talk about okay, what the attenuation coefficient is, that's just going to give you one little thing that I will just write over here. That we know that okay, as attenuation was determined by two factors, where one was the path length And the second one was the frequency, right? Okay. Clear? Okay. And we already know that, okay, yes. That both of these fellows here were directly proportional to attenuation. Okay. Now, guys, just keep in mind, yes, okay, attenuation coefficient is just going to be a way of expressing the amount of attenuation that a sound wave undergoes. Clear? Okay. But how do we define an attenuation coefficient? So, yes, okay, it is the attenuation. And if you guys didn't know, you guys, okay, still don't know what attenuation is, we can say that's a pi decrease in the power, intensity, and amplitude. Okay, okay. So attenuation coefficient, it is going to be the attenuation that the sound wave undergoes. And here comes just, okay, why we call it a coefficient. Call what the coefficient here is, okay, what stand for is after, let's say it's okay, at a distance of 1 centimeter. Now let us just look at this on a scan. Let's say this here is our scan that we have, right? Okay. And what do we have here on the side? We may have, okay, these markers here which compare the distance or depth of one centimeter. Did you guys get that?
Yep.
Good. Okay. And we can mainly say it's okay, just so we know it, okay, yes. This depth here is okay, that's going to be, it's okay, a depth of 1 centimeter. This level here will be 2 centimeters. This level here will be 3 centimeters. We can say it's okay, this level here would be 4 centimeters. We can say it's okay, this level here will be 5 centimeters. Clear? Okay. Now, what your attenuation coefficient is going to be is, well, okay, we have this transducer here, is okay, which produces a sound wave. Okay. It produces a sound wave which has a certain power, intensity, and amplitude. And we mainly say it's okay. Now, as this sound wave is okay, has traveled to us okay, a depth of 1 centimeter. What is that? We already know that okay, this 1 centimeter here is okay. This sound wave here may have come across different tissues, right? Right? Okay, some fat, some skin, some etc. Okay. Okay, maybe some fibrous tissue and so on, so on, so on, which are all going to just okay cause their own degree of reflections, a little bit of scattering, a little bit of okay, yes, absorption. But we mainly call that okay, yes, there will be a difference in the power and intensity and amplitude of the sound wave here versus here at a depth of 1 centimeter. Clear? Okay. So that degree of attenuation that the sound wave went through is going to be as okay after traveling a depth of 1 centimeter is what we call an attenuation coefficient. Did that make sense? Likewise, well, okay, as the sound wave is okay, will proceed. And okay, as will undergo as okay, a certain weakening for the next centimeter. The sound wave will proceed and undergo as okay, a certain decrease for the next centimeter. Okay. Did that make sense? So you can mainly say, okay, per centimeter, the amount of attenuation that a sound wave undergoes is going to be referred to as an attenuation coefficient. Did that make sense? Okay, now guys, one thing. Okay, one thing is that, okay, as this attenuation coefficient here is going to be considered to be constant. So your attenuation coefficient is going to be considered to be constant. So if you get a question, where it says, well, okay, yes, a sound wave produced by a transducer, blah, blah, so on, so on, so on. So has this much of an attenuation coefficient, let's say is okay, 4 decibels per centimeter. What that will mainly mean that, okay, as for each centimeter that the sound wave travels, it is going to, it's okay, reduced by 4 decibels. Okay, so that's going to be, as okay, be considered to be constant. So attenuation coefficient is constant. Did you guys get that?
Yep.
Yeah.
Okay. So at each centimeter, yes, okay. Per centimeter that that's okay. The amount of that's okay attenuation per centimeter. That's going to be as okay, what we call attenuation coefficient, and that will remain constant. Okay, but if you, for instance, say here that okay, yes, in this instance, we can say, okay, that we had 4 centimeter, or we had 4 decibels per centimeter. Okay, so your unit for attenuation, that is going to be decibels, which is okay, are going to be the unit for attenuation. Okay, but remain says okay that the coefficient here is okay represents what we call per centimeter. So that will be as okay the unit of your attenuation coefficient. Clear? Okay. Now in this case, as okay, if you get a question like this, your attenuation coefficient is going to be the same. So if it was 4 decibels per centimeter at the first centimeter, it's also going to be 4 decibels per centimeter at the second. It's okay from between the second and third centimeter, and so on. Clear? Okay. Whereas if you are asked that what is your total attenuation, then you can say, well, okay, yes, we had, okay, yes, 4 decibels per centimeter. Right, okay. That was our attenuation coefficient, which mean that we attenuate by 4 decibels per centimeter. But the total is going to be as okay, mean we can say as okay, the attenuation coefficient multiplied by the path length. And what is our path length here? Is okay, that was 5 centimeters. Okay, so your total attenuation in this instance here will be, we can say, okay, putting it this way, 4 decibels per centimeter multiplied by 5 centimeters, which means it will become a total of 20 decibels. Clear? Okay. Because your total attenuation means that okay, there's going to be a plane attenuation. If you write 25 or 20 centimeters per decibel, that may mean that you think that your attenuation coefficient is 20 decibels per centimeter. That was not the case. Clear? Okay. Or you can even say, okay, how not, why not decibels per centimeter? Because being the unit of is okay, your total attenuation. First of all, it's okay, total attenuation is just plane attenuation. Okay. After yes, okay, when taking into consider yes, okay, the overall path length. Okay. But you can also see yes, okay, the unit for your attenuation coefficient, what decibels per centimeter. Okay. There you can maybe say this counts out this, so you're still just left with this unit here. Where you mean it's okay, just multiply these two numbers and get 20. Okay. Which means it will be that okay, yes, if your attenuation is 4 decibels per centimeter, how much will your sound wave have attenuated after traveling a distance of 5 centimeters? That will become yes, okay, your total attenuation. Did you guys get that? But the unit for your attenuation coefficient is decibels per centimeter, because that's when yes, okay, what it talks about. How much does the sound attenuate after traveling 1 centimeter or per centimeter? Clear? Okay. Whereas when you say as okay, total attenuation, well, okay, yes, you may need to know as okay, how much did the sound wave attenuate per centimeter? And then you can say as okay, how many centimeters did the sound wave travel? Did you guys get that?
Yes.
Okay. Or you can put it this way. The amount of calories that you burn after walking a mile. Okay. You can say calories burned per mile. That is going to be, that's okay, that's okay. A exercise coefficient or something. Or whatever you want to put it as. Clear? Okay. But then you say, okay, I walk 5 miles, I walk 10 miles. So if I burn this many calories per mile, how many calories did I burn after walking 10 miles? Clear? Okay. But the number of calories that you burn per mile is constant in this instance here. Did you guys get that?
Yes.
Okay. So if I say, well, okay, you burn 20 calories per mile, then, okay, yes. How many calories did you burn if you walk 5 miles? That would be 100 calories, right? But then that would be, as okay, the total calories. Okay. But those, that's okay. 20 calories per mile, that's going to be as okay for each mile. But that number remains constant. Did you guys get that? Okay. Now, if you just look at it, guys, because, okay, all that's okay comes down to your relationships. Okay, this got a little bit crowded, so, okay, let me just, so what did we say? We said that yes, attenuation coefficient. But we mainly said, okay, yes, as far as the attenuation is concerned, we can say, okay, that is the reduction in the power, intensity, and amplitude, which we mainly as okay, just called attenuation. Okay. Per centimeter that the sound wave had traveled. Which means it gave us this unit here as okay as attenuation. Decibels per centimeter. Now, what I said earlier was that we can see that okay, yes, the general attenuation, yes, okay, there was directly proportional to what we call the pattern. And that same attenuation was also, yes, okay, directly proportional to the frequency. Now, guys, in your attenuation coefficient, when we talk about the attenuation coefficient as an entity of looking at your degree or amount of attenuation, that path length is fixed at 1 centimeter. Right? Because what the attenuation coefficient as an entity of attenuation mainly as okay has done is it has fixed the distance that the sound travels at in relation to is okay the degree of attenuation that it undergoes as fixed 1 centimeter. Is that clear? Is that clear, guys?
Yes.
Yes.
Good. So what are we left with? We can then only say that, okay, yes. Let's do it this way. The color effect. There's your attenuation. Coefficient is going to be, it's okay, directly proportional to frequency. Did you guys get that?
Yep.
Right, okay. So attenuation coefficient is going to be directly proportional to frequency. Okay, and you can say that's okay. Of course, that's okay. The greater your attenuation coefficient, the greater will be your total attenuation of regular attenuation. Okay. Which as a whole, if you say it's okay, if the total distance that, okay, as we scanned for was 5 centimeters, 8 centimeters, 10 centimeters, of course, in that case, okay, the path length is going to have, yes, okay, it's just okay, own effect on, yes, okay, increasing the overall attenuation. But as far as attenuation coefficient is concerned, the path length is fixed for 1 centimeter because it talks about how much the sound wave attenuate per centimeter. That's what we call attenuation coefficient. Okay, okay. So your attenuation coefficient is not going to be related or directly proportional to your path length. Your attenuation coefficient is not directly proportional to the path length because the path length has been fixed in your attenuation coefficient. But your total attenuation is going to be, as okay, directly proportional to your path length. Okay. But generally speaking, yes, okay, your attenuation coefficient is going to be directly proportional to the frequency of the transducer. Which of course then also called, well, okay, yes, the greater your attenuation coefficient, the greater will be your overall attenuation. Did you guys get that?
Yep.
Good. Now, in your book, guys, you may see an equation that says attenuation coefficient equals to frequency, and please keep in mind that this frequency has to be as okay expressed in megahertz. Divided by 2. Very important equation. So guys, if you have a frequency of any transducer, that's how you mean is okay, will be able to just okay calculate a somehow attenuation coefficient. Okay, which is going to be how much is it that this sound wave here is okay will decrease in power of amplitude and intensity and amplitude per centimeter. Yeah, okay. Okay. But you can't say that okay, the unit for this is then going to be as okay megahertz by 2. No, that's just how you calculate it. The unit for your attenuation coefficient is still going to be as okay decibels per centimeter. But you can mainly take any transducer and you can say it's okay, we have a 2 megahertz transducer. Now if you divide this by 2, what is going to be your attenuation coefficient? 2 divided by 2 becomes 1 decibel per centimeter. Now we can just take a higher frequency transducer. We can say it's okay, a transducer of, let's say it's okay, 6 megahertz. Okay, you divide that by 2. So what's going to be your attenuation coefficient here is going to be 3 decibels per centimeter. Yeah, okay. You can go even further and say, okay, what about a 10 megahertz transducer? Now that will mainly mean that, okay, yes, it's going to, yes, okay, have an attenuation coefficient of 5 decibels per centimeter. Okay. Now what does that mean? That, okay, yes, for each centimeter, okay, that the sound wave travels, yes, okay, there will be a lowest attenuation per centimeter, or the lowest attenuation coefficient. Here we have, okay, the sound wave intermediate, and here is going to be the highest attenuation per centimeter. Clear? Okay. But in all 3 cases, okay, for our total depth or the total path length was 3 centimeters in each case, for instance, we can say, okay, our total attenuation in A was going to be 1 decibel per centimeter times 3 centimeters. So yes, okay, is going to be 3 decibels. Here was 3 decibels per centimeter. But for a depth of 3 centimeters, so that's going to be 3 centimeters. Okay, 3 decibels per centimeter multiplied by 3 centimeters, our total attenuation is going to be 9 decibels. Where here we can say as okay, it was, okay, our attenuation coefficient was 5 decibels per centimeter multiplied by the total depth, which is 3 centimeters. So our total attenuation is 15 decibels. Did you guys get that?
Yep.
Okay. Now, likewise, yes, okay, from this equation here, and that's mainly yes, okay, or yes, okay, you very likely yes, okay, can be asked about that. Okay, but you can mainly yes, okay, figure out from this equation here that we can mainly say yes, okay, that if we do it this way, say yes, okay, your attenuation coefficient equals to yes, okay, the frequency divided by 2. That's why they also say it's okay that attenuation coefficient multiplied by 2 is equal to the value of frequency. Just numerically. Okay. Now some of you say, okay, how do we get this from this? Well, okay, it's an equation, so mean it's okay, just multiply both sides by 2. Here, this cancel out this, and your attenuation coefficient multiplied by 2 equals your frequency. Yeah, okay. Now, please keep in mind, guys, that, okay, yes, this here is mainly as okay for our soft tissue. I know it's been a little while that we haven't talked about or mentioned the soft tissue. But what was it that we had said that the soft tissue was? That was that intermediate tissue that we made up wholly and solely as okay for ultrasonic purposes. Clear? Okay. What did we call, okay? When did we come across different tissues? When we talked about the different propagation speeds, right? And there was a list that I told you, right? Okay, now you didn't have to remember all the values of the different speeds of the sounds in different tissues. The only value that you had to remember was the speed of sound in soft tissues. Okay, you remember that one? Okay, so what is the speed of sound in soft tissue then?
$1,540. I can't remember the units.
Oops. Well, you are more than welcome to pay me that amount of money. Oh, dear.
Is it meters per second?
Meters per second. Okay, so the $1,540 that you're going to bring, half of that goes to Caitlin, okay? And I check the other half. Here you go. Ah, just playing there, okay? So, yes, ladies and the gentlemen, if you look on your page 86 in your book, you guys have your books with you? Good. And what do you see besides that's okay, a whole bunch of paragraphs? You see a box or a table, right? Okay. Where manias, okay, goes from top to bottom. I mean, it's okay, it goes from top to bottom. Oh, shit. Don't do that. And it says water. Then it says, okay, fluids such as blood, urine, and biologic fluids. Now, ladies and the gentlemen, yes, okay, when we say biologic fluids, what would you mean by that?
Like amniotic fluid.
Okay, amniotic fluid. What else? What else could be a biologic fluid?
Well, aren't blood and urine both biologic
Blood,
fluid?
blood
Oh.
is a biologic fluid as well, right? Okay, good. What else?
Yeah,
Well,
cerebrospinal fluid.
how many up?
Cerebrospinal fluid.
Cerebrospinal fluid, okay, CSF, okay. Pericardial fluid, pleural fluid, peritoneal fluid, things like that. Okay, urine is not a biologic fluid. Okay. But then we go fat. And then we see as okay, our favorite. Soft tissue. Then we go back to yes, okay, what we can call is okay, things such as muscles. We then have okay, things such as bones and lungs. And we say it's okay here. And guys, if you go in this order here, start here in this direction, that is your attenuation in an increasing order. Whereas if you go in the opposite direction, then we start from here and go up here, that's going to be as okay, your attenuation in a decreasing order. Did that make sense?
Yeah.
Okay, so what is that we see that okay as our soft tissue? Is there as okay something that is going to be as okay intermediately as okay attenuating, not attenuating as much as ear and bone and lungs. Okay, but not as less as water or blood and other biologic fluids. Okay, so what is it that you guys will need to do is remember this. Now it's up to you whether you remember it in a decreasing order or increasing order. Clear? Okay. And just for a repeat, if you get a list that say that's okay, let's ask, okay, is this in an increasing order? And you see something as okay that it says blood, then you see as okay, soft tissue, then you see bone, and then you see ear. And there are questions asked, is this true or false? It is true. Is that clear?
Yes.
Right, okay, because blood is still as okay, lesser than soft tissues, which is lesser than bone, which is lesser than ear. Okay, so it doesn't have to write, okay, we don't have to write water. Okay, it doesn't have to, as okay, necessarily mention things such as, it's okay, fat here as well. It doesn't have to, as okay, necessarily measure or mention, as okay, muscles here as well. It just asks, okay, are these just okay if you go from blood to soft tissue to bone to ear? Is that in an increasing order in terms of as okay in accordance to attenuation? Yes. Clear, okay. But if we, for instance, okay, had put blood here, that's okay, written blood here, for instance. Of course, that's okay, then that will be false. Because then we will say, okay, the correct to say that soft tissue as less attenuated than bone, that's okay, that's correct. But blood is not more attenuating than bone. Okay, so in that way, yes, okay, it becomes false. Did that make sense? Clear, okay. Or you can simply be asked, that's okay, which of these two tissue, or which tissue here has the greatest attenuation? Okay, which of these tissue here has the greatest attenuation? Now let's just be clear about it, guys. As far as the bones are concerned, the major degree of attenuation, or we can say, okay, the major process that contributes to attenuation in bone is absorption. Clear? Okay, okay. But we also say as okay, what the hell was it? Lungs. And the major reason that lung is a highly attenuating tissue is not absorption, but rather scattering. Clear? Did that make sense? Any questions? Now, if you look at the last paragraph, on page 86. Can you see that? Now, attenuation is muscle, especially is especially interesting. Now, attenuation properties in the muscle vary depending upon whether the sound waves are traveling along or across the muscle fibers. Clear? Okay. Sound attenuates twice as much when traveling across the muscle fiber as when traveling along the muscle fibers. Now, what the does that mean? Let's look at that. And okay, guys, what you guys can do is please mark this paragraph. This last paragraph here. Now, before I get to that, I'll talk about this thing here. Can you guys name an organ where we had muscles and those muscles ran in different directions?
Stomach?
Stomach. Now, what do we have in the stomach, my dear?
You have longitudinal muscles, circular muscles. There's two more, right?
Oh,
No?
oh. One more. Circle around a long ways and yes. Oblique. Which was not around, which was not long ways, but rather crisscross, right? Okay. Good. Anyways, let's just look at it. So let's say it's okay, whatever. These are our muscle fibers. This is one arrangement of muscle fibers. And we can say yes, okay. And these are another arrangement of muscle fibers. Clear?
Yeah.
Okay, good. But here it's okay, we have to look at these arrangement of the muscle fiber. Let's just choose another color. So it's okay, blue and pink. So these are the main muscle fibers. Now, guys, if we take, okay, these are our muscle, or these are the directions in which our muscle fibers are running. And this is where we are scanning from. This is our transducer, and let's just be clear about that. That okay, yes, in this case, yes, okay, our transducer is going to yes, okay, send sound wave that runs like this. Is that clear? So we say, okay, this here is okay, yes, transducer A. Now in transducer A, which of these two muscles here will lead to greater attenuation and lesser attenuation? So guys, when we say it's okay, now this here, it's okay here, what is it that the sound wave does? It runs across. So here will be greater attenuation, whereas okay here, in this case here, the sound wave is okay runs longitudinal along the muscle fibers. So that would be lesser attenuation. Although they both could have been, yes, okay, the same type of muscle. Smooth muscle, skeletal muscle, or whatsoever. Did that make sense?
Yeah.
Good. Whereas, okay, if it was the same muscle, but we know, yes, okay, just scan it from a different angle. Here, very convenient says, okay, the direction of our sound wave is going to be like this. So for B, this here was the representation for transducer A. But for B, the greater attenuation, that will be for your pink muscle, because what is that we see here? That is, this is your pink muscle. Yes, okay. Okay, muscle that we have indicated by pink. Shit. The sound wave is going to run across or transverse to it will cause greater attenuation. Most likely, yes, okay, greater attenuation. Okay, greater attenuation as a result of greater reflection or stronger reflection. Whereas, okay, yes, what we see as okay is the relationship between is okay, the muscle fibers and your beam is longitudinal. So that will lead to as okay, a weaker attenuation. That will be as okay, as a attenuation. Or we can maybe say, okay, here the difference in the attenuation is mainly going to be because of, well, okay, here greater attenuation due to greater reflection, lesser due to lesser reflection, or weaker reflection. Not the same here. Is that clear? And what we already is okay, not already, but what I mean is okay, just said yesterday that okay, as a greater reflection is going to appear bright, weaker reflection is going to appear dark. So bright, dark. Although that's okay, they were the same type of muscles anatomically. Just you, but they were, yes, okay, just appeared brighter or darker because of the direction of the fibers in relation to your beam. That's what this paragraph here meant. Okay, guys. So list 6.4 or table 6.4, remember it. Okay. Water, then body fluids, and urine, then fat, then soft tissue, then muscles, then lungs and bone, and then air. That was in an increasing order. If you're going in a decreasing order, it's just the other way around. Air, lung and bones, muscles, soft tissue, fat, blood and body fluids, and water. Okay. Now, as far as your attenuation coefficient is concerned, it was the amount of attenuation that a sound undergoes after traveling a fixed distance of 1 centimeter. And that will remain constant. Clear? Okay. So it's made as okay. What was this attenuation? Made as okay, just a way of. You can say it's okay. Simplifying is okay. How attenuation can be expressed. Clear? Okay. And then we could say the total attenuation that's going to be dependent upon is okay. What was your attenuation coefficient, which is how much does the sound attenuate per centimeter? Then that's okay. Dependent upon your path length. How deep is it that your image went? Now, guys, just take a short tea break. Look at your attenuation coefficient. And please make sure that you have remembered the equation that attenuation coefficient is equal to frequency divided by 2. Okay, please mark that equation. If you haven't done it yet, do it now. Okay. Yeah. Okay. But if I give you a period of a sound wave and say, okay, what is the attenuation coefficient? From that period, you should be able to convert it into the frequency, and from the frequency then as well. Well, let me just ask you then. Is your period going to be directly proportional, inversely proportional, or unrelated to the attenuation coefficient? Is period directly proportional, inversely proportional, or unrelated to your attenuation coefficient?
Is it inverse?
Inverse, because it's inversely proportional to your
Frequency.
frequency. Okay, so higher period, lower frequency, lower attenuation, which will be due to lower attenuation coefficient. Okay, guys. Okay, and please keep in mind as for your attenuation coefficient, the distance that we look at in the attenuation coefficient is fixed at 1 centimeter. Okay, but from your attenuation coefficient, we can calculate the total attenuation, which is going to be your attenuation coefficient multiplied by the distance in centimeters. Okay, but can I give you a total depth of imaging in millimeters? Can I? Yes or no? If I say 40 millimeters is your depth of image, what would that then be in centimeters? 40 millimeters equals how many centimeters?
4.
4. So your total depth would be 4 centimeters. And if you have an attenuation coefficient of 3 decibels per centimeter, then what will be your total attenuation then? What will be your total attenuation? If the depth of imaging is 4 centimeters and you have a 3 decibels per centimeter of attenuation coefficient.
Be 12 decibels.
12 decibels, exactly. Right. Okay. Okay. What will there be your attenuation coefficient at a depth of 3 centimeters? If your attenuation coefficient was 3 decibels per centimeter, what would your attenuation coefficient be at a depth of 3 centimeters?
9 decibels.
Okay, my dear, whatever money you earned from the money given by Teresa,
Yeah, just take it away.
why? My dear, I said, okay, let me just repeat it because that attenuation coefficient remains constant. So it will still be 3 decibels per centimeter. Okay? And whenever you say attenuation coefficient, you have just, okay, the unit will be decibels per centimeter. So when we say that it remains constant, yes, okay, it's going to be, the attenuation coefficient is going to be the same no matter what depth. Because what was it that attenuation coefficient was talking about? It just says, well, okay, how much does the sound attenuate for each centimeter that it travels? That's what we call an attenuation coefficient. Okay. So we may, yes, okay, just give this estimate or yes, okay, average number of, okay, yes, a value of attenuation that the sound undergoes after traveling a distance of 1 centimeter, up for each centimeter that it travels. Did that make sense? So that value remains constant. Whether you're looking at it at a depth of 1 centimeter, the 2nd centimeter, 3rd centimeter, 4th centimeter, 5th centimeter, 6th, whatever. Did you get that, my dear?
Yeah.
Okay. But when you go as, okay, what is the total attenuation? Then you can say, okay, how much does it attenuate per centimeter? And then you go as, okay, what is the total depth of your image? Okay. So your total depth or path length, as we call it, that's going to be as, okay, directly proportional to your total attenuation. Which to begin with means, yes, okay, just call attenuation. Did that make sense? Okay. Now, take your tea break, coffee break, or just get a snack or something to snack on. Read through your attenuation coefficient, look at your table. And when we come back, actually we say 11:05. If you guys have any questions, please let me know. And if not, yes, okay, we can continue on to yes, okay, the other topic, which will be half value layer thickness. Yeah, okay. Have fun till then. Now, does anybody have any questions at this moment? Nope. Okay. Then let us just talk about yes, okay, the other way in which yes, okay, attenuation can be expressed, and that's going to be yes, okay, what we'll call the half value layer thickness. Okay. Now, guys, please, yes, okay, your half value layer thickness may also be known as, and that's what we're going to see more and more and more and more of is that, okay, yes, certain factors, parameters, etc., that we may come across may go more under more than one name. So you also have to remember these synonyms for SOK, I think. Okay, so this can also be called the penetration depth. This can also be called depth penetration. Let's flip it around. Okay. Depth of penetration. And even it's okay called a half boundary layer. But with that said, half value layer thickness, we can say it's okay, is going to be what? It says, okay, that's going to be the distance. If you don't like the word distance, that's okay. It's okay, say depth. What happens at this depth? At which the sound wave has attenuated to half of its original, or if you want to say not original, because that's okay, initial. Initial what? Original what? Power, intensity, and amplitude. Okay. Or we can say it's okay. This half here, or attenuate to half, can also be as okay replaced by what we can say is okay, attenuated by 3 decibels. And how does that equal half? We said that yesterday that a change of 3 decibels, and if that is attenuating, which means that there will decrease, actually will be equal to half of the original. Is that clear? So when we look at this, guys, now just as we did with, okay, it's our attenuation coefficient. Okay. And when we say the attenuation coefficient, we said, okay, we were relating it to, yes, okay, 2 factors that will have, yes, okay, either will have an effect on the attenuation coefficient or not have an effect. Okay, where we said, okay, out of those 2 factors, one of them was constant, and the other one was actually, okay, the one thing that we were looking for. So if we say, it's okay, that we know that attenuation is directly proportional to frequency. We also said that, okay, yes, attenuation was directly proportional to, yes, okay, what we call the path length. Now, what is going to be your attenuation coefficient? That's going to be mainly, as okay, the distance. So what your half value layer thickness is going to be as okay, a measurement of the distance at which your sound wave is okay attenuates to half its original or initial intensity. What would that mean? Let's say that, okay, as this here is a scan. We can just say, yes, okay, we have different distances here, or different, yes, okay, just get deeper and deeper and deeper. Now, let's just say here that, okay, as our, just keep an in here, okay. Simple, we can say, okay, our initial power, for instance, was, let's say, it's okay, 6 watts. Okay. So this is going to be our initial or original power. Yeah, okay. Now our half value layer thickness is going to be, what is going to be the distance that this power of sound wave or travel, which starts off with 6 watts and ends up to become half of the original, which then would be 3 watts. This distance here, that is going to be, is okay, the half value layer thickness. Did you guys get that? In this case, it's okay, what we actually is okay are going to be calculating is, well, okay, a certain distance at which what? Your sound wave has attenuated to half its initial value. So if we, for instance, say, yes, okay, this is let's say it's okay. This is 1 centimeter. It says, okay, we had 2 centimeters. We just says, okay, here we had 3 centimeters. And at a depth of 3 centimeters, that was going to be as okay, we had the power of our sound wave, it's okay, has attenuated to half its value, then okay, so half value, the thickness would be 3 centimeters. That is the depth. That is the distance at which the intensity or the power of our sound wave has attenuated to half. Did you guys get that? So the way that's okay in which your half value thickness is going to be expressed as means it's okay going to be that the distance may vary, all dependent upon, you can say it's okay, the degree of attenuation. Did you guys get that?
Yes.
Right, okay. Now mainly it's okay just to understand the relationships. So we can say it's okay, your half value layer thickness. Yeah, okay. Now we can mainly say it's okay, that is going to have okay some sort of relationship to the attenuation. Okay. And guys, that relationship is going to be inversely related. What would that mean? That would mainly mean that okay, as a sound wave that is less attenuating, or as a sound wave that maybe as okay undergoing less attenuation, will be able to travel a greater distance before it attenuates to half of its initial value. And or vice versa. So a sound wave which undergoes as okay great degree of attenuation will be traveling a lesser distance before its intensity attenuates to half of its initial. Because your half value thickness is mainly okay talking about the distance at which a sound wave attenuates to half its initial value. Clear? Okay. Did you guys get that? There, okay, as of course, in your half value layer thickness, it is going to be as okay. This layer thickness or as okay, because it's okay. The distance that the sound wave travels, that may as okay go, that may go up or down, all dependent upon as okay the degree of attenuation. Is that clear? Where we can mainly say, okay, based on that. Oh, let's do this one. attenuation. And of course, it's okay, our attenuation. Now, what did we said in the beginning when we talked about attenuation? It was dependent upon two factors. Okay, it was dependent upon what we call frequency and what we called passive. Where, okay, yes, now the relationship between half alveolar thickness and that attenuation is going to be inversely proportional to the distance that the sound wave travels. Because the sound wave that attenuates more will travel a shorter distance before it attenuates to half its initial power. Whereas, okay, as a sound wave which attenuates less will be able to travel a greater distance before it attenuates to the half of its initial power. But where we already okay know that attenuation and frequency, they were directly related to one another. So what is that we can say then is that, okay, yes, not only is attenuation inversely proportional to your half alveolar thickness, but so is your frequency also inversely proportional to your half alveolar thickness. Where you can say when you have a sound wave with a low frequency, or a transducer with a low frequency, okay, due to that low frequency, it's going to just, okay, be less attenuating, which will cause that it will be able to just, okay, travel to a greater depth before attenuates to half its initial intensity. And hence have a greater half alveolar thickness. Whereas on the other hand, if you had a high frequency transducer, now we know that that high frequency transducer will lead to just, okay, a greater attenuation. And the greater attenuation will cause, the greater attenuation that a sound wave is, okay, will undergo is going to mean that it will travel a shorter distance before it attenuates to half its initial intensity. Did you guys get that?
Yep.
Likewise, can we then also say that, okay, yes, this half alveolar thickness is also going to be inversely proportional to your attenuation coefficient, which may mean that a sound wave that, okay, yes, attenuates more per each centimeter that it travels. It's going to travel as, okay, it's going to recover only a lesser distance before it attenuates to half its initial intensity. Where, okay, as a sound wave with a low attenuation coefficient will be able to travel a greater distance before it attenuates to half its initial intensity. Did that make sense? Or let it just put it this way, guys. We have two vehicles. Now just pay a little attention to this example, and it's probably going to make more sense for you. Let's say that we got two vehicles. Okay. Now one of these two vehicles here is going to be a big pickup truck. Where the other vehicle is one of those small. Have you guys seen those that looks like a something like this? If you sit in there, yes, you'll only be able to fit, yes, maybe it's a packet of eggs, a loaf of bread, and maybe a gallon of milk. Yeah, okay. But what is that we can say about these two? The difference between these two vehicles here is that this fellow here, he or she is going to have a greater use of gas per mile. Whereas this fellow here is he or she is going to have it's a lesser use of gas per mile. Yeah. Okay. Now, if we just say that, yes, if we in this case is put, let's say, 10 gallons of gas in this car here, and that's let's just assume that this one here also is can fit in 10 gallons. Now, what these numbers here are, use more gas per mile, use less mass per mile. That is actually where we can equate to the attenuation coefficient. Right? Did that make sense?
Yep.
Right, okay. Now, what we now say is that, yes, this car here is only used as can only go 1 mile per gallon. Where this car here can go 10 miles per gallon. Now comes just what's going to be the half of your 10 gallons and 10 gallons? That's going to be 5 gallons. That mainly says, what is going to be the distance that this car here will be able to travel before the gas in the tank goes from 10 gallons to become 5 gallons. Well, if it goes 1 mile a gallon, it'll be able to travel just 5 miles, because before that gas, which was 10 gallons, ends up as half, which is just going to be 5 gallons. Where this car here, meaning because I can do up to 10 miles per each gallon, it will be able to travel a total distance of 50 miles. For those 5 gallons, which are going to call that yes, the contents of 10 gallons is going to become half, which is 5 gallons. Yeah, then yes, just in terms of just ultrasound can say This fellow here, okay, he was a high frequency transducer, whereas this fellow here is okay, was going to be okay, a low frequency transducer. Clear? Okay. We can say, okay, this fellow has, okay, he would have only run up to, yes, okay, a total distance of 10 miles before all gas is out. And in this car here, okay, we were able to run, okay, as a total distance of 100 miles before all the gas run out. Where we mainly can say, okay, these distances here, that will mean is okay, be penetration. Where we know is okay, less penetration is because of more attenuation. And greater penetration is due to less attenuation. But your relationships is that we can say is okay, attenuation coefficient. Well, okay, that was directly proportional to, yes, okay, your overall total attenuation, which was then also is okay, directly proportional to, as well as to your frequency. But where we can say is okay, that all these three here is okay, they were all inversely proportional to your half value layer thickness. Which means, okay, color-wise for me, this goes like this, goes like this, but then this. This, 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 but this. Did you get that?
Yep.
Okay. So half value thickness is inversely proportional to frequency, it's inversely proportional to your overall attenuation, is going to be inversely proportional to your attenuation coefficient. Okay, so you can mainly say, okay, if we for instance, okay, had two transducers respectively, it's okay, high and low frequency. You can put any number, you can say it's okay. 2 megahertz. And let's say it's okay. 6 megahertz. And they may say it's okay, and okay, as if they both have it's okay, the same. The power of the same was the same one. Okay, I guess it's okay. 20 watts, for instance. Okay. But then they will ask, okay, which of these two may have the greatest half angular thickness or the slowest half angular thickness? And it's going to be the one with the lower frequency that will be able to travel to a greater depth before it attenuates to the half. Or the power attenuates to half, which is going to be that it attenuates to a total of just 10 watts. So here we can say, okay, just for the health sake, we can say, okay, this distance here could have been 10 centimeters, for instance. Okay, whereas over here, that's okay. Our half angular thickness would have been lesser because these 20 watts was going to just okay attenuate at a shallower depth to a total of 10 watts. But we can say, okay, our half angular thickness is going to be, it's okay, where is this distance here? And we can say, it's okay, just 5 centimeters. Did you guys get that?
Yep.
Any questions? No questions?
So far, so
Okay.
good.
Pump it up.
I just said so far, so good.
Okay, let me then put a question. Maybe that hasn't hit your mind. Let's say that we have it this way, guys. We got two frequency, we got two transducers. Clear? Okay. And let's just say it's okay, 6 megahertz, 6 megahertz. So that's our frequencies, right? Okay. Did that make sense?
Yeah.
Good. Now we can say it's okay, this here is transducer A and this one here is transducer B. Okay. Now, but for transducer A, if we, for instance, say it's okay that, let's just say that our power is 10 watts. And for our transducer B, the power is 20 watts. Now the question is, which of these two transducers will have the greatest half value layer thickness? which may lure me is okay. Which of these two sound waves here is okay? Will be able to travel the longest before the power attenuates to half. So is your answer A? Is your answer B? Or is your answer A and B? Both. Which mainly mean that, okay, they will attenuate to half the initial power at the same depth.
Be both.
So you say both. Okay.
I'll say both too.
You go with both too. Okay, guys, everybody should cross the board.
A and B.
You go A and B both as well.
I also say both.
You also say both. Okay. Yes. Christina and Angelis and Jennifer, please cast your votes.
Both.
You go with both too as well. Okay.
Both, yeah.
You go with both too. Okay. Yes, Jenny. Okay, guys. All of you owe me $10. You know why?
Tell us, Mike.
Listen. Now, when we say it's okay, a greater voice, with greater power, right? Okay. Now, although it's okay, we can just say it's okay. A sound which is going to be more audible when we talk in terms of human ears, right? Or louder voice that's going to be able to travel to a greater distance before its intensity is okay, reduces to half, right? Whereas, okay, if it was a sound with a lesser intensity, or it's okay as far as audible sounds are concerned, lesser loudness will travel a shorter distance before it intensity attenuates to its half, right? Did that make sense? So when we look here, guys, out of these two, if it had been B, not B for both, But this one here, no, sorry, A, sorry. No, yeah, B that will be able to, yes, okay, travel at greater distance before it attenuates to, yes, okay, 10 watts. Because it has to lose 10 watts. Here we just had to lose 5 watts. Did that make sense? Did that make sense? So guys, if you increase your initial power, that sound will be able to, okay, travel to greater depths before its power is reduced to half. Did that make sense? Each of these cars here was, okay, as traveling, or we can say, okay, using same amount of gas per mile. Clear, okay, but if in one car you put 50 gallons and in one you put 100 gallons, then, okay, yes, which car will be able to travel a greater distance before it attenuates, okay, reduces to half the value? Of course, the car which has more gas. But in this case, it has, okay, had the same fuel economy because the frequencies were the same. Okay, so by increasing your power output, by increasing your intensity of the sound beam, what is it that you're doing? You're pretty much, okay, sending more energy into the patient. Okay, so the more energy is, okay, will be able to, okay, travel greater and greater and greater and greater distances before it's, okay, it either attenuates to half or completely attenuates. Did that make sense? Or should we do a money example? Two of you each starts a journey at the same point. Clear? Now, one of you only got $20. One of you got $40. Clear? Okay. Now you're traveling through the same tissue. You're traveling through all those things are the same. Okay. And let's just put it this way that, okay, as for each mile that you travel, there's going to be a toll. And that toll is going to charge you as, okay, a fixed amount of money. Let's say $1. So the person who started his or her journey with just $20, that's okay. He or she will only be able to travel up to, that's okay, for 10 toll stations before it's okay. His money is halfly run out, right? Okay. Halfly used. I used to half. The only is left with half. Where the person who started as, okay, with $40 will be able to just, okay, travel up to 20 miles before he or she has paid or used half of the money, right? Did that make sense? Clear, okay. So the greater the power, the greater will be the penetration. Lesser power or lesser intensity or lesser amplitude, lesser will be the penetration. Because a sound wave with a low power or low intensity or low amplitude is going to just attenuate at a shallower depth, because you start off with a lesser amount of energy. So you're going to run out quickly. Or quickly in this sense, yes, at a shallower depth. Where, so you start with a great amount of energy. You'll be able to just, run a greater distance before as, you run out. Or if you go on the treadmill and say, well, yes, somebody is, he was already half wasted. Okay. For how long is he or she going to be able to just, run on the treadmill? Not for much. Okay. But somebody is, who was pumped up with energy. Right, he or she will be able to just, run for, let's say, it's half an hour or so. Did that make any sense? So yes, and that's something that is mentioned here and now, but yes, but we can still say yes, what you guys would need is to know is these relationships here. Okay, so a sound wave that attenuates more will have a lower half-value layer thickness. A sound wave which attenuates less will have a greater half-value layer thickness. And what may cause a sound wave to attenuate less or more can be because of its low frequency or high frequency. Okay, which will also cause that yes, you will have a low attenuation coefficient or a high attenuation coefficient. So whether it's the attenuation coefficient, whether it's the frequency, or whether it is your overall or total attenuation, that will be inversely proportional to your half-value layer thickness. Because all the, sorry, I meant to do that, sorry. Because we can mainly say that, yes, this, and this, they are all directly proportional to one another. And it's if this is inversely proportional to this, then this is going to be inversely proportional to this, and this is going to be inversely proportional to this. Or where we can then also, let's say it's in case that all these factors here were the same, or it's that power, or you want to say it's intensity, or you want to say it's even amplitude. It's they will be directly proportional to your half value layer thickness. Because we can say it's okay. Greater power, intensity, or amplitude will cause that the sound will be able to travel for a greater distance before it halves to the initial. That's okay. Halves to an intensity that's half of the initial, and vice versa. Low intensity sound waves, well, attenuate at a shallower depth if the power or the intensity or the amplitude of the sound wave to begin with was low. Yep. What is the unit for your attenuation? Unit for attenuation is decibels. What is the unit for your attenuation coefficient? Decibels per centimeter. What is your unit of frequency?
Megahertz.
Megahertz, kilohertz. Okay, but here, so we mostly talk, okay, megahertz. Right, okay. Because ultrasound is going to be, okay, high frequency sound, right? Okay. Clear, okay. And what is the unit for your half value layer thickness? It measures the distance. So any unit of distance or length. That makes sense. Yes, guys. How is ultrasound physics going now? Oops. That's a great time span with no sound. Anybody want to say something? I don't mind.
I don't really like it.
You didn't really like it?
No, I'm excited to start scanning.
It's starting to get what there?
No, I said I don't really like it. I'm excited to just start scanning.
You will. But yes, okay, this is a milestone that you will have to cross. Okay, but isn't it? Okay. It's not more difficult than you make it. So don't overthink it, okay? That's probably as okay where you can make it that's okay more difficult for yourself than it actually is. Okay, guys. So that's why it's okay, my dear. If you got this index card here, it's okay, you'll be good. Or if you can transfer this to index card, just okay, you'll be good. Here. Okay, guys. Now, just take your lunch break. And when we come back, yes, okay, we will talk about, yes, okay, something that we call impedance. Okay. And what is this impedance here is going to lead to? Yes, okay, we'll get into that as well. Okay. So should we see that I see you guys back at 1 o'clock? Okay. Now, if you get the time, yes, okay, please try to, yes, okay, read on your half value layer thickness as well. And if you still have any questions about that and its relationships, or attenuation coefficient and its relationships, please don't hesitate to ask, okay? Okay, guys, see you at now, guys, before I try to continue. Any questions? Yes. The person who doesn't like ultrasound physics.
No questions yet, but
Okay.
doesn't mean they're not coming.
Sum it up.
I said I have no questions yet, but it doesn't mean they're not coming.
Okay. Did you come across something during your lunch break that make you or may make you like ultrasound physics?
No.
Okay. So, okay. Now, let's look here. Good. So one thing now, although it's okay, we will probably it's okay be getting to this topic here is okay in details tomorrow, but since it's mentioned, let's just do it. So there is okay, although your book mean is okay, just talk about it's okay, reflection and transmission. But you understand infection, reflection, sorry, and transmission, we also have to just okay understand one other thing which is going to be okay what we call an incidence. So let's just look here. Guys, this here is okay is your transducer. Now we can say it's okay that we may have different tissues here. Yeah, okay. Now, let's make this thing here a little bit colorful. Now, an incidence. There is going to be is okay any sound wave that travels towards the tissue. Yep. So that will be as okay what we will refer to as an incidence. So we can say it's okay. Sound wave that travels towards the tissue. Did you guys get that? So we can say it's okay. In this case, it's okay. This is our incidence. Clear? And we know that, okay, this is going to have, okay, as a certain power intensity and so on, so on, so. Any doubts?
No.
Good. Now comes the next thing, which is going to be the reflection. So what would be the reflection? We can just do it over here. What would be the reflection? You can say, okay, the sound wave that returns to the transducer, okay, from a tissue boundary. That is what we will call a reflection. Did you guys get that?
Yep.
Yes.
Okay. And what we can say that, okay, as the reflection is going to be, well, okay, in most instances, okay, it is going to be as, okay, part of, because it's, okay, power of the incidence is going to get reflected. So some of the energy that was going to, yes, okay, that was carried by the incident sound wave is going to get reflected. And what we mainly as, okay, just can say is that whatever is left will be a transmission. Did you guys get that?
The transmission goes all the way through, right?
Let's put it this way, my dear. Our transducer here is, okay, what did it do? It produces a sound wave, right?
Right.
Good. Okay. Now that sound wave is, okay, as it travels towards a tissue layer or tissue boundary, if that's what you want to call it, we will refer to that as an incidence. Did that make sense?
Is it incidence or impedance?
No, it's incidence.
Okay.
I know, yes, okay, incidence is mainly as, okay, what you will see later on, but mainly as, okay, to understand what the blue reflection is and what a transmission is, you will have to understand as, okay, what an incidence will be.
Okay.
Okay, but the details are counted upon as, okay, incidents and so on, so on, so on. So we will talk more about that tomorrow. Okay, okay, but we can say, okay, part of the energy or some is, okay, greater or lesser amount of the energy that your incidence was carrying, okay, is going to get reflected back towards the transducer in the form of a reflection after that incidence hits a tissue boundary. Did that make sense?
Yes.
And whatever energy is, okay, whatever sound wave is left, because it's not going to be all of the energy that is hitting the tissue boundary that's going to, yes, okay, reflect back. Okay, a bigger or smaller portion of that is going to reflect back. Whatever is left will continue as a transmission. Did you guys get that?
Yeah.
Good. But if you now look, you can say, yes, okay, what was this transmission here mean? Yes, okay, it just becomes a new incident, right? Because of course, that's okay, that's now heading towards another tissue boundary, right?
Right.
Right, okay. So we can say, it's okay, this become a new incident, then okay, as when it hits the boundary, this will produce its own reflection. And whatever was left of, okay, as what started as the transmission for the first incidence, which just become the second incidence, whatever energy is left is going to just, okay, continue as a new transmission, which just become, okay, as a new incidence. And that's how it goes on.
So
Did you Did you guys get that?
so the transmission is the energy left from the incidents?
Yes.
Okay.
Yep. You start your day with $100 in your pocket. Clear? Good. Okay. You start traveling. Okay. Now you may come across, let's say it's okay, the first gate that needs to open. Clear? Okay. What do? The gate may say, well, okay, you know what? I'm going to open only if you put $15 in. Did that make sense? Okay. That will be as okay the amount of money that you put in, and okay, as that gate opens. Now just think of that amount that you put in the gate is going to just okay be sent back in a form of a reflection. Okay, so you started with $100, you use $15 to open the first gate. What do you have now? $85. So that's going to be as okay where you will be carrying onwards. Clear? Okay. That'll be as okay what we can call as okay transmission after passing through the first gate. But once you pass through the first gate, you are mainly as okay just heading towards another gate. So that transmission just becomes a new incidence. Did that make sense, my dear? Okay, but what is it that you have now? You only got $85. Now you may go on to the next gate, and okay, this is a little bit more expensive gate. That gate may say, well, okay, I'm going to charge not just $15, I'm going to charge $50. Did that make sense? Clear? Okay. So after that, well, okay, yes, what are you going to just okay use, or what is going to be the amount that you have left is going to be as okay the transmission after passing through the second gate, and means okay to become a new incidence. So you had $85, you paid $50, you are left with $35. Did that make sense? Okay, so you can mainly say, okay, the more energy that you pay off at each gate, which means that are going to be as okay, we can say it's okay, causing the more or less is okay attenuation. But practically or theoretically, it's okay, we may say, okay, we contribute that loss of the energy in forms of reflection. Okay, or refer to that as okay as the energy that is going to get reflected back. Okay, it's going to be dependent upon us, okay, how heavily is it that this gate here told you. Did that make sense? Okay, so whatever you start with is incidence. You hit a boundary, a certain amount of this, okay, your starting amount is going to just, okay, get reflected back, and whatever you're left with, you mean is, okay, just transfer, or it's okay, are able to travel as a transmitted wave. But transmitted wave just becomes just, okay, new incidence because it's just heading towards an other boundary. Did you get that? Okay, so if we just look at it in a scan like this, okay, or in a scan, and we just, okay, just label as, okay, boundary, we can say, okay, this is boundary A, this is boundary B, this is boundary C, for instance. So A, okay, will be here, B will be here, and we can say, okay, C may be here. Because, okay, up here, yes, okay, that's where you had your transducer that was sending down, yes, okay, an incidence. Incidence. Okay. Some energy was, okay, as reflected back as a reflection. And that energy that was reflected back as a reflection, that's going to be as, okay, what you will see in your scan. Like that. And but whatever is left from this incidence is, okay, mainly is, okay, just continues on to the next boundary, which just becomes, yes, okay, a new incidence. Because what was it that we said that an incidence was? A sound wave that traveled towards the tissue boundary. So as long as, okay, yes, your sound wave is traveling, okay, it will still be as, okay, an incidence. Okay. But if you say, as, okay, if this was your first incidence because it travels towards the first tissue boundary, we can say, okay, then this here will be your first reflection, because that's the reflection from your first tissue boundary. And we can say, okay, this will be your first transmission. Did that make sense, my dear? But this first transmission, mainly because it now just heading towards, okay, as your second boundary, a boundary B, that first transmission actually is, okay, now becomes as, okay, a second incidence. Did you get that, dear? So when that second incidence is, okay, hits the second boundary, or we can label it as boundary B, yes, okay, what is that going to do? Produce a second reflection. Okay, and whatever is left of that second incidence after the second reflection is just going to be the second transmission, which just becomes just, okay, the third incidence. Because it's heading towards the third boundary, or boundary C. And that's how it goes on. Did that make sense? Okay. And what's going to happen at each tissue boundary, if you can put it this way, it may toll you more or less. Clear? Okay. It may toll you more or less. Clear? Okay. Now we talk impedance. Now we can talk impedance. Because what is that the impedance is going to be? The impedance that is mainly going to be not incidence, but yes, okay, as some of you earlier asked, incidence or impedance? No. Impedance. Now I know that, okay, yes, we can actually, okay, do this thing and say, it's okay, what is the impedance? That is going to be the resistance that at tissue boundary, or we can say, okay, any medium offers to the sound wave. And the reason that I wrote it with blue is that, okay, that is going to be that sound wave that hits a medium. Did you guys get that? Okay. So what is impedance going to be? It's going to be the resistance that any medium offers to an acoustic wave. Or in this instance, if we can say, to your incidence. Did that make sense? Now, looking at the rooms that you are sitting in, I may see somebody who had their doors closed or shut. And somebody else, okay, may have their doors opened. Now, guys, let's put it this way. If you want to walk through a closed door, what would that be like? You're probably going to bang your head or bang into that closed door. And at some point you'll say, F it. I'm going back, sitting in my chair. Clear? Because that closed door is okay, offers a max resistance for you to be able to pass through. Clear? Okay. You may have a door that is open. Now, if that door is fully open, there is no resistance. You can walk through that door without any resistance being offered. Clear? Okay. Did that make sense? So you may, yes, okay, will be able to pass through with no hindrance. Whereas, okay, yes, a door which is more or less closed is going to, yes, okay, offer more or less resistance for you to be able to pass through that. So that resistance that a sound wave experiences as it travels from medium to medium to medium to medium to medium to medium is what we will call the impedance. Did you guys get that? Okay. Now, your impedance is something that is being calculated and not measured. Clear? Okay. So impedance is going to be something that will be calculated and not measured. And how do we calculate the impedance? There is a formula, and what it mainly says that, okay, yes, that impedance is equal to the product of two things. The density. Clear? Okay. And please yes, okay, what we mean by is, okay, say, when we say the density, it's pretty much, okay, we can say, okay, the density of the medium. Is that clear? Okay. Now, the reason that I use the word medium here, because, okay, this impedance is going to just, okay, be brought up again in another chapter. Okay. But in this chapter here, since we talk about, yes, okay, sound that is traveling through the tissue, we can say, okay, here is, okay, by the medium, we mainly is, okay, will remain the tissue. Is that clear? And that is mainly as okay going to be multiplied by your propagation speed. Propagation speed of what? Propagation speed of sound in that is okay, whether you call it medium or which in this case is okay, we're referred to as the tissue. Did you guys get that?
Yeah.
Okay. Now, dear guys, as far as the unit or what we call an impedance, that unit is going to be as okay something that we call rails. Yeah. And this unit, this unit rails here is going to as okay be designated by the letter Z as in zebra. Okay. Now, what is going to determine the impedance here? Well, okay, it is mainly as okay going to be determined by the medium through which, yes, okay, the sound wave travels. For our instance here, yes, okay. Yes, okay. For this chapter here, we can say it's okay, the tissue. Did you guys get that?
Yes.
Good. Okay. This was the least important info. Clear? Okay. Okay. The real stuff is now. So if some of you want to know why and they even start talking about this impedance fellow here. Any clue? Blue clues? No? Let's just look at it, guys. And let's get this is our transducer. Okay. Let's just say that we have let's say it's okay, two tissues here. Two tissue boundaries here. Okay. Now we have an incidence. With a certain power. Clear? Okay. That incidence is okay, hits this tissue here. And this tissue boundary here is okay, what is that going to do? That is going to offer us, okay, some sort of impedance, resistance to this sound wave here. Clear? Okay. Just to as okay, be able to as okay make our comparisons, we can say as okay that we also have okay as this impedance here, which just will hit this tissue boundary here. Where this tissue boundary here also is going to yes okay offer a certain impedance to this sound wave here. Now, guys, the main importance is that all dependent upon how much impedance a tissue offers to the sound wave will determine whether we will have a weak reflection, as we may as okay see this instance here, or whether we have a, we can say it's okay, a strong reflection. Yeah, okay. So yes, okay, where we had, for instance, okay, a weak reflection. Well, okay, we can make it okay. Most of the energy of your incidence is going to just okay continue as a transmission. Whereas if you had a weak, strong reflection, well, okay, more as okay, a greater portion of okay the energy in the incidence is going to reflect it back, which means okay, will leave us with a it's okay lesser transmission. Here. So, guys, a tissue with a low impedance is going to produce a weak reflection. Where, okay, as tissue with a great impedance is going to produce a strong reflection. And guys, you can do it this way and say a weak reflection that will be dark. Whereas, okay, as a strong reflection that will appear bright on your screen. Did you guys get that? So any tissue boundary that offers a great impedance here, a great resistance to the sound wave, more energy that that incident wave was carrying is going to get reflected back. And that will cause that reflection will appear bright. And mostly as okay, as a result of that, you will have a greater attenuation at that tissue boundary, right? Compared to yes, okay, if it offers yes, okay, a lesser resistance. Lesser energy is going to be reflected back. And that reflection will appear as a dark reflection on your scan. Did you guys get this much? Yes, those of you who have an open door You will not have to put a coin or XYZ amount of money into the door to open it, right? Clear? So you can walk through. If it is open, but not open to the extent that you'll be able to pass through it freely, you may have to put in some money to just open it a little bit more. Or you're losing less money, you're paying less money. And those of you who yes, okay, have a door which is closed, well, okay, that door will need more money to open. Or you can say it's okay, offer a greater resistance. And if you realize that, okay, your door is closed, the lock is broken, and somebody even is okay, throw the key off in the Atlantic Ocean. And you may come back and you sit in your chair and say, F it, I'm not going to leave my room. Clear? So greater impedance, that's the bottom line, guys. Greater impedance, we call that, okay, greater amount of the incidence. I know it's a lot of I words. Okay. Greater the impedance, greater amount of the energy of the incidence will get reflected back. Clear? Or a greater portion of the incidence will get reflected back. And that will produce a brighter reflection. Lesser incidence, lesser amount of the impedance, lesser amount of the energy of the incident wave is going to just, okay, be reflected back. And that will lead to a darker reflection on your scan. Did you guys get that?
Yes.
So the whole importance of your impedance, is greater impedance, greater resistance, you say F it. I'm coming back and sitting in my chair. I'm not leaving this room here. Okay. Whereas if there's no incidence or no impedance, well, okay, you can walk in and out, or through that door without any hindrance. Yeah, okay, then you won't come back. Any questions? Okay. So the unit for incident impedance, the unit for impedance is rails. It is symbolized by the letter Z as in zebra. Clear? Okay. Okay. And it also goes as, okay, under the synonym or nickname of characteristic impedance. That's not difficult to figure out. Clear? Okay. It is calculated but not measured. So how do we calculate it? We calculate it by the product of density and the speed of sound in whichever media we are talking about. Now, since in this chapter is, okay, we are mainly talking about is, okay, the interaction of sound wave and media. And what is our media in this case here? Tissues. Okay. But the reason that I use the word media generalized to talk about impedance is that in a later chapter, we again come across the word impedance or term impedance. But where that is not going to be, it's still going to be media, but that media is not going to be your tissues. That's going to be the media of your transducer. Or some media in your transducer that will offer some sort of impedance. Clear? But you can say good is good, but then too much good is. And how do we reduce those impedances? Yes, okay, we have our little toolies moolies. Any questions? Nope. Now, guys, what I see is, okay, we have some 17 very nice questions regarding attenuation, R-value, layer thickness, and impedance. Now, should we try to look at them together? Does that sound like a good plan?
Sure.
Good. And we can, yes, okay, if we have missed out on something, it's okay, we can always try to bring that up as well. So we say question number 1, okay, yes. So name the 3 components of attenuation. Now they already gave us the term, but it's okay. The word component may not be accurate, so we can mean this as okay, that's going to be the processes, and that's going to be reflection, scattering, and absorption. Here. Now, question number 2. Now, as the path length increases, attenuation of ultrasound in soft tissue. Now, yes, okay, you don't go with the first soft tissue because what they mainly says, okay, where's the relationship between path length and attenuation? So as the path length increases, that we go from a depth of, let's say it's okay, 3 centimeters to 5 centimeters, or 5 centimeters to 7 or 8 or 10 or whatever. What's going to happen? This sound is going to, is okay, be increasingly attenuating. Because these 2 dudes here is okay, they were directly proportional. Did you guys get that?
Yes.
They could have put any other tissue besides soft tissue. They could have said bone. They could have said fat. That's not the question. That's not the point. Yeah, okay. Now, attenuation in lung tissue is less than, greater than, or the same as the attenuation of soft tissue. And that's what we mean is okay, you can say it's okay, or this that I said. And I mentioned it yesterday that okay, as lung is going to be as okay, having attenuation, which is probably as okay, one of the greatest attenuating tissue. Says okay, attenuation of lung is greater than that of soft tissue. Yeah, okay. Even bone would have been greater than soft tissue. Even things such as, okay, muscle would have been greater than soft tissue. Okay. Whereas, okay, what is going to be lesser than soft tissue is going to be things such as water, which is going to be as, okay, blood, body fluids, okay, and PP or urine, and fat has attenuation, which is less than soft tissue, or we can say soft tissue has an attenuation which is greater than these. Okay, now question 4 just says, okay, attenuation of bone is dash of soft tissue. It's okay. We have bone here, so that's going to be greater than soft tissue as well. Okay. Attenuation of air is dash attenuation of soft tissue. Well, okay, air was, okay, as the most attenuating media. Okay. So that's mainly as, okay, where you can say as, okay, especially as, okay, for lung and air. That's where it's okay. There's a great difference between, as, okay, your propagation speed and your attenuation. Okay, but because that's why it was for your propagation speed is okay, air and lung was lower. Then we had fat, then we had, okay, a soft tissue and so on, so on, so. Then we got to muscles and bones and so on, so. Now, what is the unit of attenuation? Mainly because that's what we have talked about is, okay, unit for attenuation is going to be decibel. But attenuation is not going to be the only factor, only parameter that is going to be expressed using the unit decibel, because this is mainly going to be, this mainly is a relative unit. In the sense, okay, what is that we are relating to? Start and end. Yeah, okay. But when start is greater than end, there is going to be negative decibels. Whereas, okay, if it is the other way around, that end is greater than start, there's going to be positive decibels. This thing here is okay, or this phenomenon is okay, we'll talk more about that in chapter 14. Yeah. Question number 5. No, not 5, sorry. Question number 7, sorry. And that's a true and false. Now, in a given medium, attenuation is unrelated to the speed of sound. That's true. Clear? Okay. Okay. That could have been false had it said impedance instead of attenuation. Because impedance of sound in a certain medium is going to be as okay related to the propagation speed. right? Well, as far as, okay, the attenuation of a medium is concerned, it is not related to the speed. So it'd be true to say that, okay, yes, propagation speed is not related to the attenuation. Did you get that?
Yes.
Question number 8. Now, what is the relationship between ultrasound frequency and the attenuation coefficient in soft tissue? So how is just, okay, our attenuation coefficient related to the frequency? And we said that they were directly proportional. Because the higher frequency, the greater the attenuation coefficient. Or vice versa. Okay, or just says, okay, from the formula, well, okay, what do we have? This attenuation coefficient was mainly, okay, being calculated by dividing frequency, which is the numerator, by 2. So whatever we calculate is always going to be directly proportional to, yes, okay, whatever is the numerator in the equation. So whichever way, yes, okay, you want to look at that one at. Here. Any questions so far?
No.
Good. Now, what is the unit of your half alveolar thickness? Now, just remember, guys, it's okay if your half alveolar thickness, the actual thing that we are talking about is the layer thickness or the thickness. Thickness of what? Thickness of the tissue through which is, okay, the sound wave travels before its power attenuation, the half value. So this thickness here is going to be as, okay, in a unit of distance, which could be centimeters, millimeters, whatsoever. Did you get that? Question
Yeah.
10. Good. Now, as frequency decreases, so we have a decrease in frequency, that will lead to, yes, okay, they are asking, yes, okay, what's going to be the change, or how is that going to, yes, okay, affect the penetration? Now your penetration will increase. You can mainly, yes, okay, just smuggle in, you can say, yes, okay, reduce in frequency will lead to, yes, okay, lesser attenuation, which will lead to increased penetration. Yeah. I mean, you can say the word penetration is, okay, to what depth is it that this sound wave is, okay, here will be able to travel before it starts to attenuate to a mention-worthy extent. Now, as path length increases, the half boundary layer. Now, some of you are going to say, what is a half boundary layer? Now, half boundary layer is made as, okay, what we also call as, okay, the half value layer thickness. Yeah, okay. Now, what they mainly mean to say here is, okay, as if the path length increases. What is going to be as, okay, its effect upon your half value layer thickness? Well, guys, this remain the same. Because it doesn't really matter whether you, yes, okay, set your image depth to 10 centimeters. Or let's say it's okay, 15 centimeters for that case. If that sound wave was okay, as tended to, yes, okay, reach a half value layer thickness at a depth of, let's say, 5 centimeters. It will do the same over here. Did that make sense?
Yes.
Okay, guys, now just look at the remaining questions and okay, we can look at them together tomorrow if you guys want to, or if you guys are good, we can just, okay, carry on. Okay. So what did we talk about today is, okay, the real main chunk of chapter 6. So please make sure that you know that. And before starting tomorrow, it's okay. I don't know how much geometry you guys have done in your schools. Not advanced, like, okay, not crazy formulas and so on. But please make sure that you know what different angles are. Clear? That's all. See you guys tomorrow.
Bye.
Bye-bye, girls. Bye-bye, guys. Sorry.